here from California. I mean, I grew up in the South, but I'd gotten used to the kind of rain that they kind of have out in California. When I moved here, I said, I got to get a bigger umbrella. Okay, so let's see. This morning I have a demonstration here set up to try, and it's been a little while since I've tried this one, but so hopefully it'll work. This is just the a piece of plastic, clear plastic here with a wire that is bent here, so it's below the plastic, comes up above the plastic, and then goes back down into the plastic. So this is like two wires here, if you can imagine, one going this way, one going that way, and now it's hooked up then to a current source, and I have a switch over here to turn it on. Currently there's no current in it. Right at the moment, there's no current flowing in this. I'm going to turn the current here. And these metal filings here, they should be iron, I expect. Doesn't say. Some kind of magnetic filings on there. And we're going to study dipoles, magnetic dipoles. You've studied electrostatic dipoles. We're going to study magnetic dipoles after the end of Chapter 3. We have a lesson on electric and magnetic dipoles. Electric dipoles orient along the electric field lines. Magnetic dipoles do the same, and you'll study that when we get to this. So I'm telling you that's what you're going to be seeing here. You're going to study dipoles here in a little bit. So when I turn this on, you should get these filings reorienting themselves. If they're free enough to turn, they should orient themselves along the magnetic field line direction. So we have effectively two wires with current flowing in opposite directions. So you should see the magnetic field lines from that. Okay, it only does it right near the wires there. It didn't change much around anywhere else, did it? But you can see around here, it's the filings are shifted here. Let me try shaking it up again, and we'll see if I can concentrate them around the without getting them touching too much. Try it again. Okay, did it a little bit. You can kind of see that. The region of influence is not very big, but you can see the field lines going around the, and that's just, I can get a little bit closer. All right. You can see here how the filings on either place here are arranging themselves tangentially around that. Okay. So I'm going to try, but it's not a very strong field here because we just have this two lines. So I'm going to try it here with a wire loop, a single wire loop, and this should create a dipole field. Right, when you have a wire loop, as you've read in the book, a single wire loop creates what is a dipole field. It's a lot like it's analogous to the field around an electrostatic dipole. So this should look a lot like the field around a natural magnet, at least outside of the loop here in this region out here. It should look like a natural magnet, resemble that. Okay, and I'm going to add a little bit more filings because our previous demonstration showed that the field's not very strong with the strength currents that we're using. There's a good safety reason for not using currents that are much stronger. Okay, so I'm going to hook this up now and try it, turning on the current. And, almost nothing. Is there anything? I didn't see anything going on there. Did anybody pick up anything there?
It doesn't seem like...
Doesn't even seem like there's anything going on.
It was sparking before, and now it's not.
Oh, did we lose the...
And this isn't changing.
Did I lose my source? I don't know if I turned it off and reset it. Let's see here. Okay, I may have... It's possible that I lost my... how would I... let's see here. This is a portable source. How do I turn it off? plugged into anything. So it's a portable source. I don't know how to reset it.
Did one of the clamps come undone?
No, this is still on. And this is plugged in. These are plugged in. But there's no sparking at all. Yeah, it's like I killed my source by holding it on too. I probably held it on too long, held the current too long. I should have just touched it. And I don't know how to reset this thing. Here we go. No, that didn't. Whoa. What was that, I wonder? Okay. No. I don't know what I'm doing with this source.
Might be the power.
Yeah.
Looks like it's got the power.
All right.
Just complete reset.
Evidently
Is
not.
the circuit not completed?
No, the circuit looks like it's complete, but I'm not getting any juice.
Could it be that thing? That one?
What, this?
As the whole plate.
Oh, the plate itself?
Because the other plate worked.
The other
this
plate
one
worked.
didn't.
I don't see anything wrong with it. Looks pretty simple. It's possible that Mr. Miller is speculating somehow that this is defective. It's not a complete circuit somehow. I don't see anything wrong with it. It's pretty hard not to get that to work. Oh, wait. It is. It's broken. Yeah, the solder is broken here. Okay, I can put it over here. Now it's making contact, so let's try it. All right. Very good, Mr. Miller. Let's get it back in view of the camera. Now let's try it. Yeah, got the spark. Okay, now you can see some of the field lines around that loop. Okay, it's not very strong, but you can see the kind of the reorientation of the filings near the wire. And now the one that has a more pronounced effect here is the solenoid. Here it is. I have a nice solenoid. Now the field strength should be much greater here because I have a lot of windings, right? The current flows in a more concentrated region. So I should have a more pronounced effect here. So, and the strength of the magnetic field inside is going to depend on the number of windings, how dense the windings are. If I get more windings, then I get a concentration of the magnetic field in that region. So, there we go. You can see the realignment there. Okay, so that shows the solenoid field pretty well. It demonstrates that there's a more intense magnetic field inside the solenoid than we got with either of the other configurations. Okay. Okay, so let's see. Go over some of the homework problems. The schedule is, as I recall, the schedule is that we've got one more homework assignment due Monday from Chapter 3. Then there's a practice test. We'll go over and review stuff in class on Wednesday, and then an in-class test on Friday of next week. It will cover predominantly Chapter 3, but some of the previous chapters can be included in that, and especially the comparison between electrostatics and magnetostatics. So there's some similarities and some differences, and that's what that test will highlight. Yes, sir, Mr. Friedman.
Was the test pushed up from the original assignment sheet?
No.
I thought it was on Monday.
Is it on Monday? Am I remembering incorrectly?
I think there might be another homework on
There's
this.
another homework? Okay, I might, hang on here, wait a minute. I can check this. Should have just put the assignment sheet on here. Let's see, there we go. Yeah, see, that's when I have this thing open, I can't open documents. There we go. Okay. Let's check. Okay, so there's a homework due on Monday, which is worksheet on curl and curl of grad and div of curl, catalog of electrostatics and magnetostatics. Then there's a worksheet on A and B by a line integral, and then there's a practice test on Friday. Yes, you're right. The next Monday, thank you, 29th, is when the test in class is going to be. Okay, thank you. Okay, so okay, so we're covering magnetostatics, continuing our discussion of magnetostatics. Good time to review what are the conditions for the magnetostatics. I think I gave you an incomplete list before.
Wires don't move.
Wires don't move, and the current flows in a loop, for example, in a closed circuit, and the current itself is constant. So one way of expressing that the wires don't move and that the current density, the current doesn't change, is that the current density is a constant. That is, it doesn't change in time. So I try to use the word constant to mean not changing in time, and uniform to mean the same everywhere in space. Okay, I try to use those words. Uniform meaning the same everywhere in space, and constant referring to the time dependence. So dj dt is 0. And that covers both wires don't move, because if the wire moves, then the current density is changing from one location to the other, so that would be a change in time. And the current in the wire doesn't change. And the other condition is that the divergence of J is 0, which means by Helmholtz theorem that the curl of J is not 0, right? So that would mean that it's circulating. Okay, so that's the condition for the magnetostatics. So JC is not 0, then the curling part of J is not 0. Okay. So in the second condition, divergence of J is 0 means that the current flows in loops and that there's no end to a wire, because if there were end to the wire and the current were flowing into the end, then it would build up charge on the end, and that's not allowed for magnetostatics. Okay, so let's look at the homework now pertaining to magnetostatics. So the first problem, number 10, is just examining the components of the curl. The curl of some vector J. It doesn't have to be a current. And there are 6 terms involved in this, and he's just diagramming, helping us to diagram the 6 terms that are involved in the curl. Let's take, for example, looking at the curl in the xy plane. There are 2 contributions to the curl that would come from looking at the xy plane. So in the xy plane, I'm looking at the component of J in the x direction, how that changes with y. And I'm also looking at the component of J in the y direction, how that changes with x, right? Change perpendicular to itself. So I have 2 contributions to it. One of them is the component of J in the y direction and how that changes along x. So I have J, y as a function of x, and then how it changes, going from x to x plus delta x. And that gives me a contribution. The curl of that, if I put a curl meter here in the middle, inside there, I get that thing spinning counterclockwise, and so that would contribute to the curl along the z direction. Okay, now I could also get a curl if I have the x component of J and how it changes going from y to y plus delta y. And if it increases, that curl meter now will spin in the clockwise direction. And so that would give a contribution to the curl into the board. And if we're looking for contributions to the curl out, all the contributions out, then we would want a negative sign on this piece and a positive sign on this piece, right? So there's a contribution to the curl then along the z direction, which is the perpendicular to the xy plane. There is this piece and the negative of this piece. So that's 2 terms contributing to the curl in the z hat direction. And then there's 4 more terms which have to do with the other 2 planes, the YZ plane and the ZX plane. And they're all of the same type. That is similarly constructed. Does that make sense? Okay. Now the next question is dealing with looking at how it is that 2 natural magnets can repel each other, and how that is a simple expression of Ampere's law that we understood before, that like impeti attract and opposite impeti repel. I can consider a bar magnet like this, and as I said, the reason that this thing is magnetic is the full understanding of this is really rather subtle. But we can understand we can produce a magnetic field like that by having a current carrying wire, carrying loop in this direction. Okay. Looking down on it here, the North Pole, looking down on the North Pole would be like looking down on the current carrying loop like this. And this would produce a field very similar to that natural magnet. So that would produce a field very, very similar to that natural magnet far away. Not up close, but far away. So this would produce what's called a magnetic dipole, and he investigates that field in the text quite a bit. And the magnetic dipole, the magnetic field lines curve around like this. And that's the magnetic field as produced by that little loop, okay? And that looks like a north pole and a south pole. Okay, so if we were to put a second magnet, you know by experience, by playing with these things, that depending on how you orient the magnets, you can get them to repel each other or attract each other. So we can understand that in terms of the basic principles we've already learned about magnetism. Suppose we align them with the poles together like this, similar like poles like this. Well, that would be like putting two of these loops together with current flowing in the same direction. So why would that repel each other? So let's look at the way to understand that is to look at how the pieces interact with each other. And so let's consider, well, there's a piece of this wire which carries current and a piece of this wire which is carrying current. Those are the nearest pieces. And we also have this piece is interacting with this piece, and this piece is interacting with this piece, right? Let's consider all of those together. So the strongest interaction takes place from the pair that I first showed you. This piece with this piece, and the current in this one is flowing this way, and the current in this one is flowing that way. So the strongest interaction is between those pairs. And what kind of interaction is that?
Repulsive.
That's repulsive. Now there are other interactions that will be attractive. This piece interacting with this piece, that's attractive, but it's weaker. We also have some other repulsive interaction. The farthest pieces from each other are of the opposite type, so those are repulsive. So, but that's the weakest piece. But on the whole, the net here is repulsive interaction between these loops. It wants to push apart. Now, if we flip one of the magnets up in the other direction now, let's put the south pole paired up with the north pole. Now we can look at that by, I should put this down here. We can look at that by flipping over the current in one of the loops. So we have this loop is going in this direction here, the same, but this one is going in the opposite direction now. And now the current in the nearest neighboring parts, the parts that are closest to each other, that are in the same direction, what kind of interaction is that? Attractive. Now it's attractive. So that will tend to pull together. So that's very qualitative, you know. We haven't actually demonstrated that the net works out the way that I have, right? We've got contributions we have to add up and make sure that the net still is repulsive or attractive, but it does work out that way. Of course, another way you could configure this is to put loops in this fashion. Currents are flowing head to tail like that, so that the North Pole is close to the South Pole. That should be attractive. And that you could understand by putting these two loops like this. Stack them like pancakes. The currents are flowing in the same direction. And each little piece of the wire loop has a neighbor here which has got current flowing in the same direction. It's close to it. And so and you add that up all the way around, that should be a nice strong kind of attraction, right? Whereas if you flip one of the magnets over, it's like making current flow in the opposite direction in the loop. Now we have a repulsive interaction. So now you can see why if I flip this one upside down like that, that's like making current now flow. I have this pancake stack here, but current is flowing in opposite loops, and those loops should repel each other now. Keep that in mind, because when we do magnetic induction, we're going to demonstrate this understanding. This will come back. Okay, so here's an interesting thing that now, if we have just a uniform magnetic field, how would we generate a uniform magnetic field? Inside of a solenoid would be one possibility. There's another possibility for generating a uniform magnetic field, a simple way. That's in your reading. That would be to take two plates carrying current in opposite or similar directions. No, they would be in opposite directions, right? That would generate a magnetic field, uniform magnetic field between the plates if you're far from the edges, and no magnetic field outside. So that'd be two different ways of generating a magnetic field. Okay, so let's suppose I have a region with a uniform magnetic field, and I'm going to represent that by a bunch of field lines for the magnetic field. Let's say the magnetic field is pointed out of the page like this. So B comes out here. So this is the XY plane. B is in the Z direction. And it has some strength B naught, which is uniform over this region. And now let's take a charged particle, a substance with charge, a body with charge, and I'm going to first let's just place that body in this magnetic field. So this body has charge Q. What happens to it?
Nothing.
Nothing. If I place it there at rest, it remains at rest. Doesn't matter how strong the magnetic field is, nothing's going to happen. Remember, this is a static magnetic field. It's not changing strength in time. It's uniform. Okay, now let's give it some impetus. And the result is, of course, now it moves. It has some velocity as a result of having some impetus. Now there's going to be a force on this. And remember, the force for a charged body moving in a magnetic field is that, QV cross B. So what is the direction of this force now?
The
E
third
cross.
direction.
What, pardon?
The third direction.
Yeah, and that, so up or down?
Down.
Yeah, it's down. So the force will be this way. If you do your right-hand rule there, V cross B will be down. So the force is down. Now notice that the force is perpendicular to the velocity, right? It's always that way because it's V cross B. So this force is perpendicular to the velocity. Okay, so now it's going to try to give it downward impetus. It will give it downward impetus, which means that after some time later, the particle will have some downward impetus, and in fact, it's moving in that direction. Now what is the direction of the force? Again, it's still perpendicular to the velocity. So it's that way. And as it continues to move around here, I'm going to draw it following a circular trajectory here. The force will be that way. The force is always pointed radially inward. It's moving on a circular trajectory. And the force is radially inward. That's like what we had before when we had a circular orbit around a gravitating body, right? The moon in circular orbit around the Earth. The force was always radially inward. And the magnitude of that force is Q over C VB in magnitude, where V is perpendicular magnetic field. So the force is just QVB over C in magnitude. Now for that to cause circular motion, if the particle has velocity v, and let's suppose that it goes in a circle of radius r. Suppose that this thing executes a circular motion of radius r. What must the end of the particle has mass m? The body has mass m. What is the force required to keep a body moving at constant speed v, mass m in a radius orbit of radius r? Right, mv squared over r. That force must be that big in order to accomplish that circular motion. And so you can find the radius from this. So it's qb over mcv, is that right? No, upside down, inverse of that. There we go, inverse of that. Is that correct? Okay, so I did this in CGS, and the solution is in SI, so there's no C in SI. Yeah, so this is CGS. Okay, so what does the kinetic energy do?
The rate of transfer.
Well, yeah, that's what the kinetic energy is. What I mean is, what is it? Is the kinetic energy going to change? The impetus changes, but not in magnitude. And the kinetic energy does not change. The impetus is that is, it has just as it loses rightward impetus, it's gaining downward impetus, so that the total momentum is constant. Okay, but so let's go back and examine this. Remember, work over a finite over an infinitesimal displacement is F dot dr, and that results in a change in kinetic energy. Now, the displacement dr is accomplished by moving at a velocity v over a short time. So this is v, f dot v dt, and we just demonstrated that f is perpendicular to v always. So this is 0. So that says that the kinetic energy does not change. In magnetostatics, the magnetic field is said to do no work because the displacement, the force is perpendicular to the displacement. True only in the magnetostatic case. It's correct to say that the magnetic field doesn't do any work. Okay. All right, so I'm going to add a little piece here. It's kind of interesting. Let's suppose you have a solid like this. Remember, we said that if you get current flowing, current J, that might be because there are parts of this body that are present, virtually present, that are said that may have positive charge, can be associated with positive charge. So you could get this current by moving positive charge to the right. You could also get positive current to the right by moving parts with the opposite charge to the left. And that would also accomplish a positive charge. And it's difficult. So far, we haven't discussed how you could tell the difference. There's an interesting way to do that, and it's called the Hall effect. I can tell the difference between positive parts and negative parts by doing this Hall experiment, this Hall measurement. So the way I do that is I take my piece of material and I put a battery connected to it, so I get an electric field flowing in this direction. So I have a battery here, positive to negative. I get an electric field in the material, and that causes current in this direction. Now let's suppose for a moment that the current is as a result of the positive charge is moving to the right. So I have positive charges moving in the material to the right. Okay, ordinarily they would just move to the right. But now I'm going to put this device in a magnetic field in the direction that I just showed you. So I'm going to place now a magnetic, all of this is in the presence of a magnetic field pointing out of the board here. Okay, now as the charges move to the right, remember they have a force downward, and so that tends to push the positive charges down. And as a result, the positive charges have accumulated here on this side and exposed negative charges up here. Remember, we're assuming that the positive charges are mobile, but there's a neutralizing set, positive and negative charges, just as much positive parts as negatives in measure, and that if I pull the positive charge away, I expose the negative charge that's present. You can think of these as the negative charges are not mobile and the positive charges are moving in this way we're thinking about it. Okay, now that produces another contribution to the electric field. In what direction? Actually up. Right. So there are two components of the electric field now. There's the part that was added by the battery, and there's this part that's added as a result of this polarization that's taken place in the material. So this is the external electric field, and this is generated internally as a result of the magnetic field. Motion in the magnetic field has generated the second electric field. And that will counterbalance the magnetic force now. Right? There's a magnetic force downward. The total force acting on these charges is a combination of the force due to the electric field and then the force due to the magnetic field. And so there's two of those terms. And so the force because of the magnetic field is now balanced by this new electric field, which is because of the polarization. And so now the charges just move to the right. But notice that it's generated charge across the material. I have a negative side and a positive side. I've accumulated charge on the surfaces, and I can measure that. That's measurable. You can go in and measure the voltage across that, voltage difference with a voltmeter. Okay. Now, remember, we're doing this supposing that the mobile charges are positive. So let's suppose that it goes the other way around. Same setup. I have an electric field this way, and I have a magnetic field that comes out of the page here. But now let's suppose that the mobile charges are negative. So I have these negative charges here, and they're moving to the left. What's this direction of the magnetic field force now? The force due to the magnetic field?
Down.
Down again. Yeah. The velocity is opposite, but the charge is opposite. So it's the same force. It's in the same direction. Also down. Okay, now that's going to push the negative charges down. So the negative charges accumulate on the bottom surface, and that exposes positive charges. Now remember, we're saying that the positive charges are now fixed, and the negative charges are mobile in the material. And so that polarizes the material in the opposite direction. Now we get an electric field in the opposite direction, but remember, the charge is negative, so the force is in the opposite direction. So that actually balances again the magnetic force, and now we just get motion of the remaining charges in the same direction. Okay, the negative charges. So you can tell by measuring this potential difference between the top and the bottom whether you have a material that has positive mobile charges or negative mobile charges. Most metals, the large majority of metals, I guess maybe. I don't know of any exception. I think in principle you could have an exception, but metallic systems, they're negative mobile charges. I guess you could have some exceptions to that. Insulating materials can be of both types. You can have, it may look like they're positive mobile charges in this thing, in this kind of measurement. The Hall measurement would reveal that the mobile charges look positive. The reason behind all of that, you have to understand the nature of solids and the bonding between solids and the role that electrons play in bonding the whole thing together. And so that's a topic for the third semester, next semester. Okay. Okay, so okay, finally, we're going to do then a kind of comparison between electrostatics and magnetostatics in terms of the different kinds of sources that are present. So, let's go through this here. We have a point-like source which has spherical symmetry. And then we have a cylindrical symmetry, which is a line source, and then planar symmetry, which is a plate source. So in the case of the electrostatics, I can put a point charge here, or I can take a charge and distribute it along a long line, or I can take charge and distribute it uniformly over a plate. And I want to look at the fields close to the middle, away from the ends in these second two cases. Okay? The strength of the electric field goes like 1 over the distance squared in this case. In fact, it was Q over D squared. The strength of the electric field in this case was 2 lambda over distance, where lambda is now the charge divided by the total length. And who remembers the electric field in this case? Plate, I have an area density here.
2 pi sigma.
2 pi sigma, right. Okay, and phi complements this, right? Phi is the integral of the electric field, and I know some people are getting a little confused. The integral of 1 over x is the log. The derivative of 1 over x is 1 over x squared, or negative 1 over x squared, right? Don't get backwards on that. Okay, so phi then, remember, is the integral, negative integral of E. So phi goes like Q over D. How about phi in this case?
QLND.
Yeah, natural log
yeah.
goes like natural log, and there's actually, okay, yeah. So I'm not worried about getting the signs right in any of this. I'm just looking at the dependence on distance is what I'm mainly interested in here, so I'm not going to be careful about signs. How about the phi around a plate?
2 pi sigma d.
Yeah, 2 pi sigma d, yeah. It increases linearly away from the plate. So that the gradient of phi, negative gradient of phi gives E, and the integral of E gives, negative integral is phi. Okay, so that's the electrostatics catalog that I'm wanting you to remember. And notice in the electric field you go from -2 to -1 to d to the 0 power, right? And phi goes from negative d to the -1 to the log of d, which is like d to the 0 power. It's not constant, but it's very slow. And then d to the +1. So try to keep that in mind. It'll help you to remember these things. Now let's do the same thing with the magnetostatics. Okay, we can't make a point-like source. Magnetostatics just doesn't exist, as far as we know. But we can make a wire carries current, and so we can do a line-like source, which is a current-carrying wire, a long wire carrying current. And the magnetic field now does not point radially outward, but points tangentially. It circulates around the wire, and the strength of that, if the wire carries current I, what is the strength of the magnetic field?
2I over CR.
Yeah. And around a plate. So in the plate, I would have, so let's see, in this case I have a current flowing in here. In the plate, I'm going to have a script I, and the script I is the current, total current, smeared out over the area. I'm sorry, smeared out over the line. I smeared out over the width of the plate there. Excuse me. Oh, God bless. Smeared out over the width of the plate. So this is the width. Let me draw that a little more carefully here. This is in the text. So let's suppose we have a plate like this, and I have current flowing. There's a total current that's now been smeared out over the width. And so now I have a density, a different kind of current density. It's not a volume current density. It's been smeared out over an area, over a width like that. And so that script I is the total current smeared out over a distance W, a width W. Okay, now the magnetic field, if I remember correctly, is that right? Have I got it right? It's proportional to that script I, the current density, and it's constant above and below the plate. As long as you're close to the middle of that plate, you're far from the edges, it's constant, like the electric field. Okay, and we also have associated with it a magnetic vector potential, or just a vector potential. the strength of A around the current carrying wire goes like log D. It's very similar. It's parallel to that. So it's very similar. There's a lot of similarity between the magnetic field strength, the electric field strength, and the scalar potential and the vector potential in terms of how they depend on the distance from the source. So make a catalog like this, and you're going to have a homework assignment where you're going to justify these entries more carefully, right? There's places in the text that you can use, and you're going to construct, from these simple solutions, you can construct more elaborate configurations. For example, you could do a coaxial cable. That is to have current flowing in one direction on an outside cylinder and current flowing in the opposite direction on an inside cylinder. The magnetic field outside, you know how to construct. The magnetic field inside is 0. A magnetic field inside of a single cylinder is 0. Just like the electric field inside of a cylinder of charge is 0. The magnetic field inside of a single cylinder is 0. So if you have this coaxial construction, you'll have a magnetic field only in between, in the region between the two cylinders here and here. So there's a magnetic field present here and nowhere else. Again, a reason for using coaxial cables in laboratories is to try to avoid stray magnetic fields and electric fields. So this helps to do that. So you can construct that from these basic cases like this. Okay. Similarly, we did the parallel plate capacitor, where you could have the same sort of thing where you have current flowing in opposite directions. And you should be able to demonstrate that the magnetic field in between is uniform and that there's no magnetic field outside. G equals 0 outside. So that's another way of generating magnetic field. Now, what would be the direction of the magnetic field in this configuration?
Into the board. In the middle.
Yes, yeah, it's into the board. God bless, into the board in the middle. Good. Both the top and the bottom push it in that direction. And so, in fact, the strength would be 4 pi script I over C inside there, where script I is the description of the current per width. Okay, so you're going to construct that. Okay, so now let's go. Any questions about that before I go on? Yes, sir, Mr. Dowell.
So, for the going back to like electric fields, like I know in the first part,
Yeah.
we used water as like a good analogy to build into that. Would it be
Right.
a good analogy for magnetic fields? Because like it makes more sense in my head, like to start at the point source and then integrate that over to get the other ones where the shell thins out. But I can't really imagine that for a magnetic field. Why the distance is relational?
Yeah, and I think you're touching on the point that the direction of the field line is not necessarily perpendicular, is not necessarily in the direction of propagation. So that in that first example where we had a point charge and the electric field pointed outward, but also the propagation was in that direction. And so we felt like then we understood the flow, an analogy to flow outward like that, because the field was the velocity field of the motion of the fluid or the volume of the material that was flowing outward, right? We made that analogy. But now we've extended it into other things, and it looks kind of funny. So, for example, but it's even true for an electric field. Let's take an electrostatic dipole. And you remember you constructed the electric field for this. We calculated what this looks like, and if it's in this direction. And let's just look at the electric field along the line, the line that bisects the two, like that, along the x-axis. If these are arranged along the y-axis, then let's look along the x-axis. The electric field looks like this. It falls off, and it goes like 1 over the cube of the distance, remember, if you get far away from the dipole. Okay, but now let's remember this electric field propagates to the right. If we swap the dipole, let's switch the sign on this. Let's make this a negative here and this a positive. Let's flip the dipole. Now that takes time to propagate outward. So after some intervening time, the electric field will have switched here. This will go up here and this will go up here because the dipole has swapped in the direction. But that will only be true in the region where I've had enough time for the propagation to take place. So this distance here will be CT, where the T is the time since I switched the dipole. And so you can see there's a transition region here. The electric field goes from up to down over a very short region, which depends on how quickly I switch the dipole. So the direction of propagation is clearly to the right, but the electric field is up and down. So now we've got something which is a little different than what we were starting with. We were considering it propagating in the same direction as it pointed. Okay? So we've extended, by analogy, we've extended this. Okay? So keep that in mind. The same is true for the magnetic field. The magnetic field around a wire, if the current is coming out of the board, is in this direction, like this. It's counterclockwise. But if I switch the current into the opposite direction, now the current is flowing into the board, the direction of the magnetic field is going to flip, but that propagation is outward. So if I swap a current in the wire, now I get magnetic field pointing in this direction for some distance. But if the distance is great enough, it swaps back to the way it was before, because these guys out here have not gotten the memo yet. The news has not reached them that the current was switched. And so there's a transition region. So the propagation is clearly perpendicular to the direction of the magnetic field. Okay, so we're making analogies here, right? We started off with the flow analogy, but we've extended that now. And so the divergence and the curl are now started off originally understanding flow like this, but we've generalized it. So you have to be careful about taking these analogies too literally. Remember, analogies have their limitations. So is that what you were getting at? Does that help pinpoint at least the thing to think about?
Yeah.
Okay. Right. Let's see. The other question that's related to that, and maybe this is good. Before I was going to start talking about Stokes' theorem, but I think maybe I'm going to start that on Monday, so I don't have to interrupt. One of the questions that came up, your list of confusions were very helpful for me, and I think for yourself also. One of the questions that came up was how to visualize these fields, and I think that's related to this question that you're asking here. How do you visualize the electric and magnetic fields, right? You don't see these fields directly. Okay, so how do you visualize them? Well, these demonstrations are intended to help you with that. But that is a question, how do you visualize them? Well, you have the same problem. Actually, maybe you had the same problem, but it wasn't in your mind that you had this problem when we studied gravity. How do you visualize a gravitational field? Really, that's kind of the same problem. Now, the electric and magnetic fields are richer because they have they can point in funny directions, and the magnetic field doesn't by itself produce a force. The receiving body also has to have impetus, right? So it's richer now. Things are more complicated than they were before. But the problem, let's go back to the case of gravitational field. How do you visualize a gravitational field?
Its effect on the bodies.
Well, that's right. I mean, that's how we would know that a gravitational field is present. If I put something there, pull up the pencil, let go of it, see what happens, right? And one way to visualize the field is to think about the force that would be present on this body if I put it here. And so now it's a vector, right? But that force in a gravitational field, if I have a gravitational field here, the force is going to be proportional to the gravitational field, right? Our little g, when we did force of gravity, our little g was like a field vector. The strength of that was the mass times that strength would give you the force on the body. So it's like a force per mass for a test body that I put in the gravitational field I find that the force is proportional to that mass, and so if I divide by that mass, then I get something that's independent of the test body, which is the field strength, and the direction is in the direction of the force. So I could draw this gravitational field now around the Earth. And it would fall off like 1 over the square of the distance. Near the surface of the Earth, it's constant. It's uniform. If you're really close to the surface of the Earth, it's uniform. But if you get farther away, it looks like that. That's visualizing the gravitational field by looking at the force per mass. This exists in the plana. The plana is altered in such a way that there is this condition, such that if I put a test body, it will have a force in a particular direction. So there is kind of a directional aspect to the field that's present. And remember, this thing propagates outward at the speed of light. If somehow I could do away with this body here and get rid of it somehow, magically, then it would take time for the news to arrive at distant points. Okay, so that's how you would visualize a gravitational field. So now maybe the electric field is the same, except that you have a test charge you're putting in place, but it's the force on a test charge, and in fact the force per Q. So that's the electric field. So I put in a test charge, and the measure of the strength of the electric field is to put something in there and see what happens to it. Okay, so that helps you to visualize maybe the electric field a little bit. Magnetic field's getting a little harder because it depends on the impetus that's present in that second body, right? So the force is going to be Q over C, V cross B. So it's got to have, as a result of having its impetus, it's going to have some velocity. And the strength of the force there is going to be related to that velocity. So now it gets a little harder to, but I can figure it out, right?